Good evening, everyone. I am Bandhuga Kurupu, Technical Events Coordinator for Civil Engineering Sectional Committee. And today is the 10th session of our lecture series on structural design of highway bridges. And we appreciate Professor Jayasinghe's willingness to share his expertise with us and his commitment to advancing the field of structural engineering. On behalf of all the participants, I want to thank him for his time, effort, and generosity in conducting this lecture series. And for the participants, kindly add your membership number as well with your login name so that IESL can trace your participation. Over to you, sir.
Okay, thank you. So today we are going to start a new topic, which is actually applicable to Sri Lanka because we have few bridges that have been constructed as continuous, and most of these designs have been done in other countries. So very little expertise is available in Sri Lanka at the moment with the practicing engineer. So I thought of actually sharing my expertise with you so that you will be able to handle continuous bridges with confidence. So the first thing that I'm going to discuss today is why continuous bridges cannot be constructed in the normal, they can be constructed, but why they cannot be designed in the normal way, and what are the special things that we have to consider. So what I'm going to show you is that we'll start handling the problem in the normal way, and then we'll see where things can go wrong and how to address those special issues. So basically I will explain all the things on the understanding that it is going to work. The normal method of designing a prestressed concrete bridge will work for continuous bridges as well. And in doing so, I will show you why it will not work. And then we will start discussing the special things. So I might need 1 or 2 lectures first in the normal way, and after that another lecture also to explain the way that we are going to handle the special issues. So I'm going to go very slowly so that you will be able to understand most of the special features and concepts that we have to understand with respect to the continuous bridges. So what I thought was I'll do a little bit of comparison when I'm talking about it, so that you will be able to see where the design of simply supported and continuous would be similar, where it differs. And so with that, I will now get the camera working so that I can draw and explain. So we say structural design of continuous prestressed concrete bridges. So we'll try to first understand the special features of continuous construction, and we'll assume that one way or the other we can construct it at once. Later we see how we handle the issue that we cannot construct it at once. So that will come later. Right. So let's say that we have 3 span bridge, continuous. So I would have to say that, in Sri Lanka, you would have seen some of the bridges where we use precast elements. And so these are all our expressways are constructed. Elevated expressways are constructed. Then we arrange the topping. And here we apply a pre-stress like that. Now this is not the type I am going to talk here. This is the real pre-stressed concrete bridge type, like the 6-lane new bridge at Kalin River or Banampitia Bridge, the old the bridge close to the Demo Company. So that is the old steel bridge that was replaced by 2 bridges. They are all that type. And so let's say that we are going to have a 2-lane bridge. Then what we generally do is we'll have a large box girder supported like this, and we'll have the pedestrian walkway here and the 3.5 meter carriageway here, and we might have a handrail here, and we can have another bridge side by side. And here again, there is a possibility. And here to make the weight minimum, we remove the concrete in the center. So we get box girders, and similarly we can also have T-type bridges. T. We can have 2 T's. Now that's another possibility. This is another possibility, but this is more common or more popular these days because people have mastered various things. So when we have a box girder like this, again there are certain guidelines that we can follow. And first we'll discuss briefly about some of those guidelines. Then you'll have a good idea of what we are trying to analyze. So basically, if you have a box girder, one thing is, you will have the top girder like that, and then it will go like that, and then you will have something going there, that, and there will be a chamfer, and you will get a section. So generally, the depth is selected so that you will have something like 1.8 meters to 2 meters generally. But we have actually constructed box girders smaller than that. The reason is, a person can walk inside without much difficulty. So that's one of the criterion that was used in the early days. So which means the span or depth ratio will be something like 20 to 26 range might be a possibility, right? And then there's another important thing, that is, the bottom slab has to be at least 175 millimeters. Because if the bottom slab is thinner than that, it is not practically possible to prevent cracking. Because, if the bottom slab is very thin, there's a tendency for some cracks to occur. Because when you provide 2 mats of reinforcement, the reinforcement becomes too close. So when you have 175 millimeters, it can have sufficient flexural strength. Then you will ask why we need a chamfer. The chamfer is to make sure that the torsional shear flows like this around the section. Then you'll ask how you get the torsion. And here you can see we are supporting it here. And this pedestrian pavement is loaded less. So we might get a situation where we have a heavy vehicle here and very little load here. So definitely this will be subjected to some certain amount of torsion. So if they is subjected to torsion like this, if it is subjected to torsion, then we need a torsional resistance. But one of the good things about these spine beams is that they are torsionally very rigid. The reason is when you look at the lever arm between the torsional stresses, induced forces, there's a huge lever arm. So even so, because of that huge lever arm, you'll find the torsional stresses are pretty small. And the torsional stresses will not go in these directions because torsional stresses will always go in a closed path as much as possible. Then we have to think, okay, what are we going to do here for the top slab? Now the top slab, you know, the thickness can be something like 250 to 300 millimeters. Why? The reason is, you know, here we have chamfers and here we have a cantilever. So we'll have to provide some reinforcement here and ensure that this cantilever can carry the load of a heavy load. Should be able to carry a heavy load because there can be a pedestrian pavement here and it should be able to carry a heavy load. So we might get some HB wheels on this. So we have to make sure, you know, the loading like 1 HB axle is about, if you are designing for 45 units, the 1 HB axle is 45 tons. So once you divide by 4, you will get 11.25 tons. So you get a very heavy load acting on the cantilever portion. So to resist that type of moments, you might need 300 to 350 millimeters at this place. Here it can be less, it can be 250. But here you need 300 to 350 to resist a heavy load like that. But certainly you can try smaller depths, provided that you are going to apply a little bit of force tension in the transverse direction. That is one possibility. And then how about this? Now we know if you are going for internal tendons, then we'll have ducts in all these locations. So we have to make sure the duct can be accommodated. And then in addition to duct, you have to ensure that this pogo vibrator can go through it. So when you look at all those things in requirements, the minimum thickness of the web might be about 300 to 350 millimeters. So this web can be 300 to 350 millimeters if you are going to anchor some of the tendons, start the tendons or stop the tendons by having blisters. So blister is something that you have the wall like this. So you want to stop a cable, so you take it out and create a blister where you provide a lot of reinforcement like this, and the cable is anchored here. So that's a blister. So by creating blisters, we can anchor the reinforcement out. But the modern trend is to go for external pre-stressing. So we might have some pre-stressing tendons outside the beam. So inside the beam, but outside the web. So depending on all those requirements, we might need 50 to 75 millimeter adjustment in these numbers. So, but generally these numbers will remain something like 300, 350, the bottom slab of 175, the top slab of about 250, and the cantilevers, the connecting point might be about 300, 350. So that will all can be optimized by when you analyze. But the most important thing is to find the cables, how we are going to lay the cable in the case of how we are going to lay the cables in the case of continuous bridge. So this is the kind of section you get, and let's assume that we are going to construct it at once. So if we construct it at once, what will happen? We'll get a bending moment diagram due to the self-weight of the structure. Due to the self-weight of the structure, we'll get a bending moment. And we call it MD due to the dead weight. Now what's going to happen? Now we have to think about how a continuous bridge responds to the live loads. But if you compare a simply supported case due to the self-weight, what do we get? We get WS square 8. Here it's much lower. Here you might get something like WS square 11. Much lower value. Now you can clearly see why the continuity is considered advantageous. Because the moment you make it continuous, what happens is the bending moments reduce significantly, because now a part of the bending moment is resisted with a hogging moment here, sagging moment here. So when you look at the total range will be about WS square 8. The range will be WS square 8. The design moment will be WS square 11. Whereas in the case of simply supported case, we always get WS square 8. Whereas in the continuous bridge, the range will be in the range of WS square 8, not the moment. So you can see there will be a clear reduction in the bending moment that you have to use for design purposes. So which means the continuity will have a very distinct advantage in prestressed concrete bridges or any other structure. Continuity is always advantageous. So today is 9th. Civil Engineering Sectional Committee, page number 1. Right, now we see what's going to happen with respect to the superimposed dead loads and live loads. Right. Superimposed dead loads. Let's assume that superimposed dead loads are also going to apply at once. If they are also going to apply at once, later I'll show you how we do the construction. But for the time being, we are going to assume that all these loads will come at once. So what will happen? You get a bending moment diagram like this. Then the live load. Again, I will use the earlier BS loads just to make things clearer for you. Then once you understand one type of loading, you can always use any other type of loading. So what I do is I will get right. So this is the, I'll use this old BS 5400 1978 loading system. So I'll share the screen and show you that. So up to 30 meters, the magnitude is 30 per lane. After that, it reduces. We just use a simple system like this to learn the theory. And then once you learn the theory properly, you can apply any kind of loading. So we just see something simple like this. And you can see you can take down this equation, that is 151 1 over L times 0.475. Right? So that gives the loading. And I'll stop share. And let's say these spans are something like 40 meters and 50 meters and 40 meters. Now that gives an indication of the kind of span range we are going to work on. So we are not going to work in the range of 30 meter, but we are now talking about 40 meter, 50 meter, 60 meter, that kind of range, right? Then what happens is now, how are we going to apply the loads in a continuous structure? So we see what are the possible scenarios. So this is one, the same beam again with a different scenario, and then again same beam, again the same beam, again the same beam, right? Now what are the possibilities? One possibility is that, you know, over the full length, we get a maximum load of HA. Now first we lead with HA. So if you look at the span length that we have loaded, 40 plus 50 plus 40, 130 meters. So we are loading 130 meters. Now we will share the screen and see what happens. So it's about 130 meters. So if I use the equation, that is 1 divided by 130 to the power 0.475 multiplied by 151. So the load is 14.9. The load I have to apply is 14.95 kilonewtons per meter. Right. So I have to apply 14.95 kilonewtons per meter. Now, what can you say about the bending moment diagram? It will go on like this. It will go on like that. Now, what is the other possibility? Another possibility is we have the maximum here, no load here. Now what can happen? The loaded length is 40 meters. Now if the loaded length is 40 meters, you can see the loaded length is continuously for only 40 meters. So over 40 meters, the equation is 1 over 40 to the power 0.475 multiplied by 151. Now you go in there, now you are applying a 26.18. You apply 26.18. So what happens? Now you get a different bending moment diagram. So you get a bending moment diagram going like that, another bending moment diagram going like that. There's no load that goes that way. So you can see, due to this loading system, we get sagging moments and hogging moments all in the beam. Now what is the next possibility? Only this one comes, 26.18. No other load on the beam. Then what happens? Then this goes like this goes this way, so this way. So in the case of a continuous beam, you are now going to get a sagging moment at the support. And you know, this can be reversed also. That is 26.18, 40 meters. Now all these ones, the continuously applied loaded length is 40 meters. Now what happens? Now you get a bending moment diagram that does this. Now, what are other possibilities? Other possibilities, only this one, that is 50 meters and 1 over 50 to the power 0.475 multiplied by 151. That is gives 23.5. Lower than. Why? The loaded length is 50 meters. Now you can see, I mean, these days we have computers to do all these things. Now just imagine, you are doing manual calculations and you get all these different types of loading. Then the life would have been very difficult for highway engineers. So now you can see a very different map. What is that? There's a hogging moments in the span. Right. So that is now with all these different diagrams with us, we just see what would be the shape of the envelope. So we have this. So this situation. Now what would be the envelope? Envelope will look like this, going like this, going up, going like this, going up, going like this. And then it will go like this, and then again you can see that will be the live load envelope. Live load envelope. Can you understand it? Now there are two important things we are learning. One is there can be so many different load combinations, load patterns, and for each pattern, then the magnitude is different. For each pattern, the magnitude is different, and not only the magnitude, even the bending moment diagram is weird because some places, generally we know at the support the bending moment is hogging, but here you are getting sagging. And then we also know in the span, bending moments are sagging. But here you are getting hogging in the span. So because of this reason, if you put all these together, we get a very strange diagram that looks like this. Bandhuga, is that correct? Is that clear?
Yes, sir.
Yeah.
That is clear.
Now we'll forget about all this superimposed load just for clarity. And now we have two loading conditions. One is let's assume we have superimposed load, dead load all put together. So we have one dead load, right? So that will take a shape like this. And then on top of that, we have to superimpose this. Then again, you have to look at the kind of magnitude of the bending moments. And you find now in a continuous structure, because we are using a massive section, this dead load is also significant. Goes like that. Bending moment diagram goes like this. So this is the dead load. Now we are going to know the end load. Now what will happen? Generally, if you have only this part, what is visible, then the bending moment will be on the lower side. But now what we have is not one path, you have a system. So which means the bending moment diagram will go like this. And on the other side, it will go like this. To go like that. Then you might ask, So how are we going to identify them? We'll call this MB. We'll call this MA. So MB is maximum moment. MA minimum moment. Okay. MA is maximum moment and MB is minimum. Then you might ask, okay, what is the range? This is the range. Let's say delta M. What is delta M? This. Delta M is that. The range. Range is that. So you can see something very different. Now in the case of simply support, when you look at simply support case, the beam will bend like this at transit. Transit will bend like this. It will bend like this in service. So when you look at the stressors, transit is important. When you look at the stressors, transit is important. Why? Because compression at the bottom can be too much and it can fail, or it can fail in tension. It can crack in tension at the top. So it's tension, here compression. Then we put it and we apply the live load. When you apply the live loads, now it tries to fail in the other way. So that's why we said, these prestressed concrete bridges, if you go for composite construction, they will have massive capacity. Because now you can see it has a big top flange and it also has strong tendons, so it's good. So we say transfer important. Now what happens here? Here you can see the bending moment diagram, minimum and maximum are not governed by the dead load moment diagram. The minimum and maximum is governed by the range of the moment that you can get due to live loads. So the range of the moment is important, and transfer is not important. Not important. Transfer represents the dead load moment diagram. Then if live load is important, we have to look at what is the pre-stressing force that is important. If transfer is important, the initial pre-stressing force is important. So here under service, R times P is not the initial pre-stress after all the losses have occurred. The pre-stress available will be R times P, where R is about 0.7 or 30% losses. So what you get now is, for one of the important conditions, P is important. For the other condition, RP is important. So just keep it in mind. But here, trans is not important. So minimum moment is also governed by RP. Maximum moment is also governed by RP. Which means, we have a very special condition. We have a very special condition. That is, the dead weight of the structure is not going to be very important, because our design is not governed by the dead load magnitude, but it is actually governed by the moment range. Is that clear?
Yes, sir.
Right? Is that clear? So this is something that is very important for us to understand. So that is the clear difference between the precast simply supported construction that we often use, where because we can't afford to have a shuttering system at the site because we are constructing these waterways and motorways and all these roads. So we cannot afford to have a proper shuttering system. So what we do is we go for precast construction and also have in situ cast wider top flanges. So you will find that they cannot fail easy. Why? Because we have a very favorable huge top flange. That's one side. On the other side, we have a very strong steel at the bottom because the steel breaks only at 1860, whereas the steel is stressed only about 920. So we can double it. That means there's a huge capacity in the pre-stressing wires, so that with minimum amount of pre-stressing wires, you can actually satisfy the ultimate moment carrying capacity in complex. There are two reasons. One is already the beam starts with some pre-stress, like bending upwards. Then you keep on loading until it fails. And when you are doing that, you find you are actually loading a member which is having very favorable conditions. So because of that reason, we always say pre-stressed concrete beams generally do not fail in ultimate limit state, and because of that, if you want, you can actually forget about ultimate limit state and do all the designs considering the service conditions. Okay? So we are going to use the same concept, but only difference is because the structure is continuous. Now the moment range is governing, not the dead load moment. Whereas in the case of simply supported one, the transfer was important. That means the initial load applied is also important. Whereas in this particular case, we are going to see something strange happening, and that is the moment range is governing, and for the moment range, or less, the pre-stress is R times P. So with this knowledge in our mind, and assuming that we know the span, we know the loading, and we have a program like SAP 2000, and because this our loading is more or less symmetrical, we can say that I'm going to analyze the whole spine beam section as one beam and get the minimums. You don't have to even go for a relation, right? Because sometimes longitudinal loads are dominating, and there's only one member. So you will find it's pretty easy for you to analyze only one beam and then get the bending moment diagrams. But I'll show you how we deviate. But for the time being, we are going for a simplified model so that we can understand what is going on. What is going on, right? Now what we do is, if this is the case, if it's so easy to get a bending moment envelope with maximum value as MB, minimum value is MA, now we should be able to design the section. We should be able to design the section. So let's see how we can design the section. To design the section, first we have to find the pre-stressing force. And to find the pre-stressing force, now we have to see whether this manual diagram, or when generally you call as manual diagram, is applicable. So we have to just see what's going on. And our question is manual diagram applicable? If it is applicable, we know straight away you can find the pre-stressing force. And the theory is manual diagram is applicable, but in a very special way, not in a normal way. So now we are going to discuss this special way. So can you understand up to this point? Vanduka, any questions in the chat channel? No, nothing on the chat.
Yeah, up to now, no questions.
Sorry, no, nothing on the chat. Yeah. So if it is all clear, I can now go to the next step, a very important step, where I'm going to look at the magnet. So shall I go to that step?
Okay, sir.
Right. So what you have to understand is, if you take any section, finding the maximum moment at that section and minimum moment at that section is not a big deal. You can just analyze it as a beam and beam on SAC 2000 and apply the loads, relevant loads, and get the answer. Because you can see pedestrian pavement loads are not going to dominate. Why? Pedestrian beam moments need not dominate because the magnitude is only 5 kilonewtons per meter squared. It's a small load. So what you can do is you can apply the full load on the pedestrian pavement, that is 5 kilonewtons per meter square, multiplied by 1.5 meter if they are having a walkway of 1.5 meter. And then as we have done here, we can find the effect of HA loading, that is the UDL, and then we combine them and apply. But when you are applying a UDL, there's something called knife edge load. So if you are interested in finding the shear force, we bring the knife edge load close to the support. If you are interested in finding the maximum bending moment in a particular span, then we place the knife edge load at the center of the span. But on a particular loading, you can't have two knife edge loads. You can have only one knife edge load. So if you take this particular first case, you have to apply the knife edge load either here or here in the center or here to get the maximum bending moment. You can't apply three knife edge loads. You can apply only one knife edge load, and you have to decide where you are going to apply it. So in this case, we cannot strictly say which one would be more critical. So we have to apply it at the center of 40 meter and center of 50 meter. But if you are interested in finding the maximum shear, then we bring the knife edge load as close as possible to the support, so that on one side of the support you get a massive load, on the other side no. So automatically the shear force diagram will be altered, right? So that's how we have to look at it. So basically with these numbers that these are actually very simplified numbers, because we have ignored HA knife edge loading, and also we have ignored HB type loading. But to understand the theory, always we have to use a reasonably simple example. So because of that reason, I have simplified it as much as possible. Now we are going to look at the equations, governing equations, and the manual diagram, and see which theory is applicable. Because we have already derived the set of equations, and actually we derived it for simply supported case, then we derived the same thing for composite action. Now today we are going to use the same set of equations for continuous construction. So what are the special conditions in our sign convention? We measure upwards y1 and it's negative. We measure downstairs y2, downwards, we measure downwards positive. Z1 negative. Z2 positive. I value positive. I is second amount of area. It cannot have negative and positive. It's always positive. Right. Now we take the section again as earlier and apply a pre-stressing force, and compression is positive. So you get POA. And because the tendon is not at the center with an eccentricity, so this is compression. So you get this is PE, and here you get upward, so you get compression here, tension here. So you get PE over Z2, PE over Z1. Here we want a negative answer, but Z1 is negative, so automatically we get a negative answer. Right? And then due to the applied loads, this is going to fail in tension in the midspan. So what happens? Then you get the moment, and if you look at the moment, right, it is one of these moments, the range, one of these moments. And when you apply the maximum moment, what can happen? If you apply the maximum moment in the span, what could happen? If you apply the maximum moment in the span, here you can see we are applying a certain moment. So we get a situation where MB over Z2 minus. Here you get MB over Z1 minus. So we'll write two equations for this case. We'll write two equations for this case. So we get for the top fiber POA plus PE over Z1 minus NV over Z1. And what could happen? This is going to fail in compression, because when you apply this sagging moment, this MB is sagging moment. When you apply this sagging moment, what will happen? When you apply this sagging moment, what happens is, you will get the beam failing with tension at the bottom. Beam failing with tension at the bottom, compression at the top. So that's what I have done. Tension at the bottom, compression at the top. So it's going to fail in. So it's going to fail in tension. So here you get the top fiber. So it's going to fail in compression. So if that is the case, it should be less than compression under working conditions. So that is first. Now you look at the bottom fiber, how it's going to fail in tension. The bottom fiber is going to fail in tension. So POA plus PE over Z2 minus MA over Z2 should be greater than tension at working. Number 2. Is that clear?
Yes, sir. So, and there's one question regarding bending moment analysis.
Yeah. What is that?
In the
There's on the chat. Is that right? Yeah.
yes.
I'm sorry to disturb you, sir. Is relating to bending moment analysis at different stages. The necessary analyze 50 and yes. Now I did not do that, but now that there can be many other cases. So that's the problem with this bridge design. So this is also a possibility. This is a possibility. The 50 plus 40 is 90. So 90 means 1 divided by 90 to the power 0.475 multiplied by 151. So you get 17.81. Now the loading is 17.81. What is the shape of the bending moment? Going to be like that, going to be like that, and going to be like that. So you get so many different combinations. So that's where the problem comes. When it is continuous, numerous number of possible combinations. Not only that, I mean, you can even have half the span loaded. So there are so many different combinations, but generally this type of combinations will be more critical. So you cut, and not only this, now you can get a mirror image of this also. So you will get about 15-20 load combinations with different lengths, different magnitudes, and very strange type of bending moment diagrams. I'm sure, I mean, you are not very familiar with this type of bending moment diagram, or this type of bending moment diagram. So we are getting so many different types of bending moment. And that's where the bridge engineers struggled a lot in the early days, because they had to do manual calculations. So they struggle a lot. Right. So here we are having a much favorable condition, because now we have computers. So it's a matter of creating a structure and then creating different load cases with different magnitudes. Computer will do the rest. And not only that, computer will even generate the envelope, because we can ask the computer to create either a bending moment diagram or an envelope. So all those facilities are there. So with those facilities, the life, the calculations that you have to perform have become much simplified. Now you concentrate more on the design than analysis, because analysis can be handled straight away by the computer, whereas design part is the one that you have to be little careful before you go for any kind of preparation for spreadsheets. Now you look at this. That is this, the minimum one, MB case, right? The minimum value. So what happens in the minimum value? Now it's like, if you look at the minimum value here, what will happen? It is like the case that we got here. The beam bending upwards, right? So we have to find a case for that, right? So this is the case, right? But what we do is, we are actually checking for a particular moment, and so only thing is, now it's going to fail in the other direction. It's going to fail in the other direction. So what happens now is, again you get the same equation, TOA plus PE over Z1 minus MB MA over Z1. Now what's going to happen? Now it's not going to fail in compression, it's going in other direction, so it's going to fail in tension, FTW. So this is equation number 3. Then you get another equation, P over A plus PE over Z2 minus MB over Z2, MA over Z2. Should be Now these the bottom fiber failing in compression. So because we are talking about a minimum, so it has to be less than F compression. Now we get again we are getting 4 equations, and if you look at this equation again, you cannot say P. All these values will be RP. Why? Because we are dealing with a situation where we are considering a bridge in use. So we will all get up because we are considering a bridge that is in use. So there can be 2 types of failures. One is this type of failure. The other one is this. So we first consider this failure. Now we are considering this particular. This will occur when the bending moment is maximum. This will occur when the bending moment is minimum. When the bending moment is minimum. So that's how you are looking at it. Right? That's how you are looking at it. So we get 4 equations.
So I think it is muted.
Okay, sorry. Now you see, so you can write this equation from this first equation, and then because E is negative, Z1 is negative, so we get the inequality in the other direction. So here you get minus Z1 away plus FCW Z1 plus MB divided by RP. So this will be equation number 5. And from the next equation also you get E should be greater than minus Z2 over A plus FTW Z2 plus MB over RP. Equation number 6. Then equation number 7 will be P should be less than minus Z1 over A plus FTW Z1 plus MA or RP, and the last equation B should be less than minus Z1 over A plus FCW Z1 Z2 plus MA divided by R. 8. So we have 8 equations like that. So same pattern like we have seen earlier, the same pattern Z1 Z2 Z1 Z2 and Z1 Z2 Z1 Z2. Here NB, here NB. Right? Very simple pattern. Same pattern, same inequality, same everything similar. So that is Y greater than C plus M X. What is M? 1 OP. M is 1 OP. What is X? That is FCW Z1 plus MB over R. What is C? Z over A. It could be Z1 over A or Z2 over. So we get a equation like that, which means again we can go for the graphical representation. We can again go for the graphical representation. sectional committee number 5, and today is 10/5/2020. Now you will find this beam, this continuous bridge design should be extremely simple. Why? Because the simple theory that we learned in the form of a graphical representation is applicable for continuous construction, and the equations are even simpler than what we got with simply supported case. Because when the simply supported case, in one equation, the pre-stressing force is P. In the other condition that is under service, it's RP, after losses. But here, everything is RP. So then we can find so many interesting things from this set of. There are many interesting things you can find about the manual. So we are going to look at those things. So what happens? So we get 1 OP, and here we are going to get E, and Z1 OA minus Z1 OA minus Z2 over A. Why? C means minus Z1 OA or Z2 OA. C as an intercept. So equation number 5 says E should be greater than. And the last two equations say E should be less than. They are right. E should be greater than. The other two says E should be less than. Yes, E should be less than. Yes. Now what we do is equation number 5 and 6 says E should be greater than. Okay, so that means says E should be equation number 5. This is equation number 6. And then we have two more equations which says E should be less than. And that means E should be less than. Number 7 should be less than, and E should be less than 8. Now we have an additional limit on the eccentricity. We cannot have tenders outside the section. So this is E max. So what is the feasible region? Like that. We get a feasible region like that. And for this to exist, gradient of 8 should be greater than gradient of 6. Gradient of 8 should be greater than gradient of 6. For this condition to happen, gradient of 8 should be greater than gradient of 6. Because 6 and 7 says E should be greater than. E should be greater than. E should be greater than means E should be on this side. And the last two equations say E should be less than. That means E should be on the upper side. So if you take the gradient of 8, that is FCW Z2 plus MA over RP over should be greater than FTW Z2 plus MB over. And then we can say Z2 times FCW minus FTW should be greater than MB minus MA, and Z2 should be greater than MB minus MA divided by FCW minus FTW. Can you see? FCW is positive, FTW is negative, this is a positive quantity. MB minus MA is again a positive quantity. So if you look at the bending moment diagram that we have drawn, this is MB minus MA. MB is say 18,000. MA is 10,000. MB minus MA is 8,000. Right? So, you get this equation. Z2 should be greater than MB minus MA, which is the range of moment. And how to get the range of the moment? We get the range of the moment from the bending moment element. This is the range of the moment. The same range here. Same range here, same range here. So basically the live load bending moment envelope will decide the range. The live load bending moment envelope will decide the range. And here you can see the section required does not depend on the dead load, but it rather depends on the range of the moment. Range of the moment. Is that clear?
Yes, sir.
Right. Okay. So, basically, now we get this equation. Now we can also look at the next equation. That is gradient of 7 should be greater than gradient of 5. Gradient of 7 should be greater than gradient of 5. So here what I'm saying is this and this. Gradient of 7 should be greater than your gradient of 5. So we look at it. Gradient of 7. FTW is Z1 plus MA divided by R. Gradient of 7 should be greater than gradient of Z1 plus MB or R. And you take Z1 times FTW minus FCW should be greater than MB minus MA. So Z1 should be greater than MB, should be less than. Why? This FTW minus FCW is negative, so it should be FB minus. So Z1 should be less than MB minus MA divided by FTW minus FCW. So just see compare these two equations. MB minus MB, FCW minus FTW, here FTW minus FCW. So what it means is, it's saying Z2 is positive. Because of that reason, it's given by MB over MA minus FCW minus FTW. Z1 is negative, so it is given by MB minus MA over FTW minus FCW. So same value. You get the same answer. The same answer. That means the moment we find the live load range, the range for the live load, that is after doing all these different load combinations, you can go for an envelope. The moment you draw the envelope, we know the range. So this MB minus MA, the range. So the range is known. For this number 5, this number 6, right? This number 7. So which means get the envelope, get FCW and FTW. When you say that get the envelope, that means you know MB minus MA. You straight away know what is Z1, was it Z2. So what I going to do? You know the range, select a section like this. Like this. Calculate Z1, Z2. This is negative, this is positive. Compare these two ones. Straight away you know whether the section is going to work or not. Straight away you know whether section is going to work or not. So you have to select a section where Z1 and Z2 values are as required according to the bending moment range. Is that clear, Bandhu? Is that clear?
Yes, sir.
So
That's clear.
basically, can you remember? I mean, I gave a chart to find the section for Y beams.
Yes, sir.
So even if a person is not a bridge engineer, straight away he can say what is the bridge that will work for a given span, right? But we don't have any chart like that for box girders. So what are we going to do? What we go do is we will not worry about the section. We'll develop a bending moment diagram under elastic conditions. And from the bending moment diagrams, we can get the envelope. From the envelope, we can get the range. And once you know the range, straight away we know in which, what is the minimum size needed. What is the minimum size needed? So we select a section which is larger than that. Is that clear?
Yes, sir.
Yeah. So basically we don't need a chart like that because you know we can't nobody can draw charts for box girders because everything is variable. I mean, that will all depend on practical considerations because we are not talking about very small members. We are talking about massive members over large spans. So the design engineer might do so many things to optimize it. Even this angle for the chamfer is not known. So that will all be decided by the design engineer. So basically nobody can develop any charts for box girders. But we don't need it. Why? The moment you draw the bending moment diagram, just having an arbitrary view and get the bending moment diagram, and then from those get the bending moment envelope, find the range, and the moment you find the range, you can get Z1 and Z2. So select a section which is having Z1 and Z2 larger than what is given by these two equations. So that's what you do. Is that clear?
Yes, sir. That's fine.
Yes. Then there are some other interesting things we can see from this. If I look at, so this is you can see this is the minimum moment. This is the intersection of equation numbers 5 and 8. And this is the intersection of equation numbers 7 and 8. And then if you look at the intersection of 5 and 6 and 7 and 8, 5 and 6 and 7 and 8. We just look at it and see what are these pre-stressing values. That is the intersection of these 2 points. These 2 lines. That is equation number 5 and 6 and 7 and 8. So let's see what are 5 and 6. What are 5 and 6? 5 and 6 is with MB, and intersection means the extensity is the same. So you can say minus Z1 over A plus FCW Z1 plus MB over RP is equal to equation number 6. That's what happens in the intersection point. So that is minus Z2 over A plus FTW Z2 plus MB over. So you find this MB over RP appears on both sides, so it will cancel out. And we have this RP. So you get FCW Z1. FCW Z1. Yes, FCW Z1 minus FTW Z2 over RP is equal to minus Z2 over A plus Z1 over A. From this, you can work out the equation for RP is equal to, this goes this way, this goes this way. F CW Z1 minus FTW Z2 divided by minus Z2 over A plus Z1 over A. From this one, P is equal to, so you can take divide both top and bottom by minus 1. Then you get, yes, okay, doesn't matter. FCW Z1 minus FTW Z2 multiplied by A divided by R, you get minus Z1 minus Z2. So this is negative, this is negative, this is also negative. So that means you get a positive answer. And let's say this point is A, this point is point A, this point is point B. So the corresponding pre-stressing force is 1 over PA. The corresponding pre-stressing force here is 1 over PB. 1 over PA, 1 over PB. Right? So this is PA. What will you get for the PB? Same thing. And PB will be pretty similar. But now let's look at what are the important things. Now, does this point depend on section sizes or the bending moment? It doesn't depend on the bending moment. Doesn't depend on the bending moment. So that means along the beam, the manual diagram will move like this in a narrow band. This PA and PB will be independent of the bending moment, whereas these points will be dependent on the bending moment. We call them C and D. C and D will be dependent on the bending moment. A and B will be independent. So now you can see, if you are selecting a pre-stressing force, in which region we should select it? We should select it in this region. Why? Because the pre-stressing forces as minimum as possible. Pre-stressing forces as minimum as possible. So you can see something very interesting. Something very interesting. That is, the along the beam, Magnum diagram is going to move like that. Because these PA and PB are independent of the bending moment, but dependent only on the section. So PA and PB will depend on the section sizes, not on the bending moment. And when you are designing, we always make sure we select a force that's as close as possible to the minimum. So those are the important things you can learn from what I have explained today. And it looks like the equations for a continuous beam appear as pretty much simpler than the simply supported case, because in the simply supported case, at transfer the pre-stress was P, under service RP. So R term would be seen in the equations, but here, R term is not very important, and it appears, but for PA and PB, R term will come. And here you can see it depends on the allowable stresses and the section sizes, it is not based on the bending moment. So those are some of the pretty interesting things. So what I have shown is that Magnum diagram is a pretty strong tool, and it is applicable for simply supported case. It's applicable for composite section. Now you have seen it's applicable even for a continuous one. But you have to be a little careful because some of these things would not appear as simple as this, and that's what people found it hard way. Although they thought, okay, so it's so simple. Later they found it's a nightmare designing a continuous bridge. But later, when I did the PhD, I developed a new method that will allow us to design this in a very simple manner. So that's what I'm going to explain in the next 2 weeks. The first, I will explain why this simple method would not work, and then I will explain how to get it work. So that's how we are going to develop the lecture series. So there will be 2 or 3 more lectures, about 3 more lectures on continuous bridge design. And once you understand this method, again you will find the design of a continuous bridge is not as simple as designing a simply supported one. But once you master it, if you can, within a reasonable time, with the aid of a spreadsheet, we can easily complete a continuous bridge design as well. So that's what I'm going to show you. Only thing is, because we are dealing with so many sections, it's very hard for us to do manual calculations for each and every section. So because of that reason, we include all these equations in a spreadsheet, and then we use the spreadsheet for our calculations rather than doing manual calculations. So that's how pre-stressed concrete bridges are designed these days. So you can easily prepare a spreadsheet in the way that you like, and then get the computer to do all the calculations. But because you know the equation that you have used, you have the full control of the process. You have the full control of the process. So is that clear, Manukka?
Yes, sir, that's clear.
Yeah.
And there's one question.
Yeah.
Something related to what is the meaning of line of thrust?
Line of thrust will come, but we have not come to that level yet, right? So in the third week or in 2 weeks' time, I will explain what is line of thrust. Or sometimes even next week I might explain it, right? Because line of thrust is something that we have to very carefully understand. to understand what is line of thrust, first we have to understand what is meant by secondary moments or reactant moments. So I will introduce reactant moments that will automatically occur in continuous structures, and actually that is the problem that happens. So basically, once you select the cable profile as per the manual diagram, after completing all the calculations, now you will find there are some additional moments that you have not considered in the design. So, which means all your calculations will be invalid. So, you complete the design to find that all your calculations are invalid. So, that was the problem. And that is the problem I have solved by developing a new design method. And when you use that method, you will not have that problem. But I will explain what is line of thrust next. Okay.
Okay, sir.
Not only line of thrust, there's something called concordant profile and actual cable profile, line of thrust, concordant profile. There are so many new terms that you are going to learn. Is that okay?
Okay, sir. That's fine.
Right. Then we conclude here. But so far it's very good because what we have done is we have repeated what we have done earlier for simply supported and composite sections.
Yes.
But when you do the same thing, you will find it's not going to work for continuous structures, and you need a special design method, and I will explain it with the aid of a spreadsheet. I might need about 3 more days to do that. Okay?
Okay, sir.
Right, okay, right.
Mm,
So shall I conclude?
okay, that's fine, sir.
Yeah, okay.
And I would
And
like
I will share this notes with you.
Okay, sure, sir.
Okay.
And I would like to invite engineer Chamit Gayan to do the vote of thanks.
Thank you, Mr. Thank you, Mr. Bandugar. I am pleased to deliver this vote of thanks for 10th session of the webinar series on the success on the structural design of highway bridges conducted by Professor Thishan Jayasinghe on behalf of the organizing committee. I would like to express our heartfelt gratitude to Professor Thishan Jayasinghe for the insightful and informative presentation. The webinar series has been hello?
Yeah, we can hear you now.
We can hear?
Yes, we can hear you.
The webinar series has been great success, and we have received numerous positive feedback from the participants. This would have been possible without the support of the CESC Chairman Engineer Mrs. Kamala Gunwardhan, the IESL Secretary, the Publicity Department, and the IT team. We would like to thank them for their dedication and the hard working in making this event success. We would also like to express our appreciation to all the participants for their active participation and the insightful questions. Your enthusiasm and the engagement have made this webinar series valuable learning experience for all. Finally, we would like to inform you that the next session of the webinar series will be held on the 16th of May. We hope to see you all there. Thank you. Good night to all.
Okay. Okay. Thank you, sir.
Thank you very much.
Thank you,
Then I'll leave there.
Thank you, sir.
Okay, sir.
Thank you. Thank you very much.
Thank you, sir. Good night. Thank you.